Hello students, welcome to Math Practice. In this fourth part on integration, we are going to study a technique called integration by parts. Many important examples are based on this technique, which is specially used to integrate product of two functions. So watch the video till the end, and also the links to the other parts on integration is given in the description box. Integration by parts is generally used when we want to integrate product of functions. The formula is integral of fx into gx dx, where fx and gx are two functions, is equal to fx into integral of gx minus integral of f dash of x into integral of gx dx whole dx. So let us first of all understand it by a very simple example, how the formula works. Suppose we want to integrate the function x into e raised to x. So there are two functions. Let the first function be x and the second function be e raised to x. So by the above formula, integral of x into e raised to x dx is equal to fx, means the first function as it is, x, into integral of second function, which is e raised to x, minus integral of f dash of x, derivative of the first function. The first function is x, its derivative is 1, into integral of gx dx. So now x into, integral of e raised to x is e raised to x. So x into e raised to x minus integral of 1 into integral of e raised to x. Again, integral of e raised to x is e raised to x. So basically it is integral of 1 into e raised to x, which is integral of e raised to x. Again, which is e raised to x. So the final answer is x into e raised to x minus e raised to x plus c. So this is how the formula works. Now see, some formulas can be derived using this technique of integration by parts. We will see some of them in the coming examples, but this is just the list of formulae. So these formulae, if you remember, it will be very easy to solve examples based on them. Okay, so we will take one by one all the examples. Example 1. Integrate the function x square plus 1 into log x. So now first of all we will simplify this function. X square plus 1 into log x is x square log x plus log x. Now to find integral of log x dx. Now see, we will find this using integration by parts, and this formula itself you can remember so that it can readily be used in other examples. It is integral of log x. Now integral of log x can be written as integral of log x into 1. Okay. So now we use the technique of integration by parts. I have given the formula down. Integral of fx into gx dx is first function fx as it is. Okay. So we have taken log x as the first function, log x as it is, into integral of 1. What is integral of 1? X minus integral of f dash of x, derivative of log x, which is 1 upon x, into integral of again 1, which is x. So 1 upon x into x will give you 1. And what is integral of 1? It is again x. So simplified form, integral of log x dx is equal to x log x minus x plus c. This you can remember as a formula. Now next step for our example. I is equal to integral of x square log x dx plus integral of log x dx. Okay. Now for the second term we have already found integral of log x. Now for the first term you have x square into log x. Takes the first function as log x and the second function as x square. Basically you can take it anyways, but generally when you want to use the formula, the function which is easily integrable, you can take it as gx, and the other function which you can find the derivative, you take it as fx. So now over here the first function is log x and the second function is x square. So first of all, the first function as it is means log x into integral of x square, which is x cubed by 3, minus integral of f dash of x, derivative of log x is 1 upon x, into integral of again x square, which is x cubed by 3, plus already we know integral log x is x log x minus x. Now just put all the values. The second term over here is 1 upon x into x cubed by 3. So the x in the denominator gets cancelled, it will become x square by 3 into its integral. So it will be x cube by 9. So the final answer is I is equal to x cube by 3 log x minus x cube by 9 plus x log x minus x plus c. Or you can group the terms having log x. So it is x cube by 3 plus x into log x minus x cube by 9 minus x plus c. Example 2. Integrate x into cos inverse of x upon root of 1 minus x square. Now since you have cos inverse of x over here, to simplify it, what we can do is we take cos inverse of x is equal to t. So cos t will be equal to x. Take the derivative both the sides. So minus sin t dt is equal to dx. Now again put the value of this in the original function. In the original function x, what is x? X is cos t into cos inverse of x is t. So the numerator is t into cos t upon root of 1 minus x square. Root of 1 minus cos square is sin. So the denominator is sin t into dx. What is dx? Minus sin t dt. So when you put all these values, what happens is sin gets cancelled. So ultimately you have minus of integral of t into cos t dt. Now you can see it is simple. Two functions, multiplication of two functions, we can use integration by parts. Take the first function as t and the second function as cos t. Put the values. Now you know what is the integral of cos. Integral of cos is sine, and the derivative of t is 1. So putting all the values, we get I is equal to minus of t sin t plus cos t plus c. Now again re-put the value of t. We had taken t as cos inverse of x. So when we re-put the value, it is minus cos inverse of x into root of 1 minus x square minus cos of cos inverse of x. Now you know cos of cos inverse of x is x. So the final answer is I is equal to minus of root of 1 minus x square into cos inverse of x minus x plus c. See, integration by parts is a very useful and important technique, but you have to just take care while doing the simplification. Third example, integrate e raised to 2x sin x. So take the first function as e raised to 2x and the second function as sin x. So now it is first function as it is e raised to 2x into integral of sin x minus integral of f dash of x, derivative of the first function. What is derivative of e raised to 2x? 2e raised to 2x into integral of sin x. You know integral of sin is minus cos. So now just put those values. So you get I is equal to minus e raised to 2x cos x plus minus minus has become plus 2 into bracket integral of e raised to 2x cos x dx. Now for the second term, again you use integration by parts. So for that you take the first function as e raised to 2x and the second function as cos x. Now why we are doing this, you will just see how simplified it becomes, because you know that integral of cos is sine and in the original function also you have sine. So let us go forward. So I is equal to first term as it is minus e raised to 2x cos x plus 2 into, now the second term, in that we have taken the first function as e raised to 2x. So e raised to 2x into integral of second function which is cos x minus integral of derivative of the first function, it is 2 e raised to 2x into integral of cos x. Integral of cos is sine. So e raised to 2x into sin x minus 2 into e raised to 2x sin x dx. Okay. Now what is integral of e raised to 2x sin x dx? It is over original integral I. So now what has become as, because you have 2 outside and also here you have 2, so you have 4i. This minus 4i you bring it on the left hand side. So you now have 5i is equal to minus e raised to 2x cos x plus 2 e raised to 2x sin x. So I is 1 upon 5 into the whole term, or you can take out e raised to 2x common. So the final answer can be written as e raised to 2x upon 5 into bracket 2 sin x minus cos x plus c. Example 4. Integrate x e raised to x upon 1 plus x whole square. Now see, here we are going to use integration by parts, and also I told you in the previous one of the slides that there is an important formula which we can derive by integration by parts. You have to remember this formula. Integral of e raised to x into fx plus f dash of x is in e raised to x fx plus c. So this is a very useful formula. Now for our example, you have e raised to x into x upon 1 plus x whole square. Now x upon 1 plus x whole square we can write as the numerator as 1 plus x minus 1. So now just break it into two terms. So first term is 1 upon 1 plus x and second term will become 1 upon 1 plus x whole square. So now our original integral I is equal to integral of e raised to x into bracket 1 upon 1 plus x minus 1 upon 1 plus x whole square. So now suppose if I take fx, a function fx as 1 upon 1 plus x, what is its derivative? You know that it is 1 plus x raised to minus 1. So derivative is minus 1 plus x raised to minus 2, or f dash of x is minus 1 upon 1 plus x whole square. So now our function has become I is equal to integral of e raised to x into our fx plus f dash of x. So just simply use the formula. Its integral is e raised to x fx plus c, means e raised to x into 1 upon 1 plus x plus c. So final answer e raised to x upon 1 plus x plus c. Next example, integrate e raised to x into bracket 1 plus sin x plus 1 plus cos x. Now over here, whenever you have functions of trigonometric type, try to apply any of the trigonometric formulas to make it into one particular form. So now sin 2x is 2 sin x cos x. Similarly, cos 2x is 2 cos square x minus 1. Instead of 2x, you have x over here. So sin x can be, these are the half angle formulas. So sin x can be written as 2 sin x by 2 cos x by 2, and cos x can be written as 2 cos square x by 2 minus 1. Now our integral I is integral of e raised to x into 1 plus 2 sin x by 2 cos x by 2 upon 2 cos square x by 2. Just simplify, take both the terms separately. So first term is 1 upon 2 cos square, which is sec square, and second term is tan x by 2. Now since you have e raised to x over here, this should come to your mind that if you take fx as tan x by 2, the derivative of tan, you know, it is sec square. So the derivative of tan x by 2 is sec square x by 2 into derivative of x by 2, which is half. So f dash of x is half into sec square x by 2. So now this is nothing but in the form of integral of e raised to x into bracket fx plus f dash of x. Integral is e raised to x fx plus c. So see how simple the final answer has become. I is equal to e raised to x tan x by 2 plus c. Next example, integrate root of 1 plus x square by 9. Now in the starting I told you there are some formulae which we can derive using integration by parts, and these formulae you have to remember so that whenever you have examples of these type you can apply it directly. So this was a group of formulae in which you had integral of root of x square minus a square x square plus a square, also root of a square minus x square. So if you have examples of these kind, directly you have to use the formulas. In this example, you have root of 1 plus x square by 9. So this is 9 plus x square whole upon 9. So root of 9, that means root of 1 upon 9, which is 1 upon 3, you can take it outside. So now it is integral I is 1 upon 3 into integral of root of 9 plus x square. So this is of the type a square plus x square or x square plus a square. In the integral I have written over here, you just have to put the values. Your x is x and your a is 3. 9 means 3 square. So just put the values and the final answer is x by 6 root of x square plus 9 plus 3 by 2 log of mod of x plus root of x square plus 9 plus c, just using the formula. Next example is integrate root of 1 plus 3x minus x square. Now whenever you have these type of problems, first of all make a perfect square and then add or subtract the remaining terms. So you have 1 plus 3x minus x square. See over here I cannot change x square or 3x, so that I keep it as it is. but the last term to make it a perfect square, that I can add and subtract. So ultimately I have the constant term 1. This one I am actually writing as 13 by 4 minus 9 by 4. Perfect. So now what we have done is our original integral we have written as 13 by 4 minus x square minus 3x plus 9 by 4. So what has happened is the second bracket has become x minus 3 by 2 whole square. As I told you, 3x you cannot change. 3x you have to keep it as it is, but using that form the last term. So it is x minus 3 by 2 whole square. Now you already have the formula root of a square minus x square. So a square is 13 by 4 over here, or a is root 13 by 2. And instead of x, I can take x minus 3 by 2. And why I can take so? Because anyway, if it is x minus 3 by 2, you put it as some another y also, it is dx will be equal to dy. So there is no need to make any other changes. So now either you can do it in 2 steps, but now since directly you know the formula, instead of x, just put x minus 3 by 2. So in the above formula, if I put instead of x, x minus 3 by 2, and instead of a, root 13 by 2, or a square is 13 by 4. Just put the values in the above formula. The final answer after simplification will become, take care while simplification. After simplification, the answer is 2x minus 3 upon 4 into root of 1 plus 3x minus x square, that is the original function. Root of a square minus a square, that is the original function. Plus 13 by 8 into sine inverse of x by a. So x is x minus 3 by 2. So it is 2x minus 3. So sine inverse of 2x minus 3 upon root 13 plus c. This is the final answer. Also now, using the same technique, I have just given an assignment example. Integrate root of x square plus 3x. This is also very simple. Just using the above technique, you get the answer. In case of any query, please write in the comment section. So students, integration by parts. I hope this important technique is clear. Please like and share the video and subscribe to the channel for the complete series on integration and math of class 9, 10, 11 and 12. Thank you.